Swayam Prabha. Digital India. Educated India.
So now the question is, what is the exact algebraic expression of this gamma in? So the exact algebraic expression for this gamma in for an nth order by maximally flat binomial transformer is given by this expression. Okay. Now as you can see, for this transformer at gamma in theta equal to pi by 2, this value becomes 0, and so this becomes equal to 0. Now if I take the derivative, say any kth, or say the first derivative, say so again what you can see is that this value will be equal to 0 at theta equal to pi by 2, and so this derivative will also be equal to 0 at theta equal to pi by 2. This way you can show that for all n minus 1 derivatives, if you go on finding the derivative of this derivative till the n minus 1th order, all those expressions will be 0 at theta equal to pi by 2, and therefore it satisfies the maximally flat requirement. Also note that irrespective of what the order is, what the value of n is, this will be equal to 0 at theta equal to pi by 2. Okay. Alright then, so now we know what is the expression for the maximally flat transformer. Let us try to find the values of this. Let us see how we can find the value of this n and a. So these are the two unknowns, right? So say we want to match our gamma in as obtained from this equation with our actual transformer, multi-section transformer. So here in this expression, depending on what our bandwidth needs are, two quantities are unknown. One is this capital A and this capital N. So we need to know what is the value of this constant A and what should be the order of the filter. Okay. Now from the graph that I had shown earlier, you can see that as the number of sections, as the order of this filter increases, in other words, as the value of n increases, the bandwidth increases. See this, look at this graph. You see that for n equal to 1, the bandwidth is only this much. Say if we take a point, any value of gamma in, say gamma in equal to 0.1. So when gamma in equal to 0.1, the bandwidth for n equal to 1 is the lowest, and for n equal to 4 is the highest. So from this we can say that as the order of the transformer increases, our bandwidth will also increases. So in other words, if we need a higher bandwidth, we have to have a higher order of the transformer. And as we shall see, a higher order of the transformer will correspond to more number of sections. Alright. So how can we find out the value of this capital A, first of all, this quantity? So to do that, we note that, find out what is, let me draw the multi-section transformer. So here the characteristic impedance was Z0, Z1, this diagram I had shown in the previous part. Okay. So here so all these transmission lines have a equal electrical length theta, which could be equal to pi by 2, which then would imply that all these transformers are quarter wavelength long, or they could not be pi by 2, which is also fine. But note that at when theta equal to 0, what happens? The electrical length for all these transmission lines, they decrease to 0, and this point is directly connected to this point. So then this implies that gamma in theta equal to 0. This I had already mentioned in the previous part. Will simply be equal to RL minus Z0 upon RL plus Z0, right? So then, but from this equation, what is the value of gamma in theta equal to 0? So let me write this equation once again. Gamma in theta is equal to A times 1 plus e raised to j 2 theta whole raised to n. So from this equation, what is the value of gamma in at theta equal to 0? So that is simply equal to 2 raised to n a. And now substituting this value here, it implies 2 raised to n a is equal to RL minus RL plus Z, which in turn implies that my A is nothing but this value. Fine? Or I can also write this as alright. The next simplification that we shall do is, let us try to find out the value of gamma in theta magnitude. So that is equal to this. Now note that the value of e raised to j theta magnitude is simply equal to 1. So I can then simplify this equation to this value. Now further I can write this as and this is equal to cos theta raised to power n. So then this becomes equal to gamma L cos theta raised to power n. So this is the value of the input reflection coefficient magnitude for a given value of theta. Okay, it's somewhat simplified. Okay, actually I should write this as, I should not write it like this. Let me should write it modulus gamma n, modulus gamma n modulus of cos theta raised to n. Okay. Now suppose we define at a particular value of theta, say my modulus of gamma in theta equal to gamma m. Okay, and I say that my acceptable value of gamma in should be lesser or equal to gamma m. Okay, so that's how we can set the bandwidth, because we had discussed the bandwidth, and while discussing we had discussed about this concept of gamma m. So suppose, again let me draw, suppose this is my gamma in theta. Okay, and say as I said, we can arbitrarily define the value of acceptable gamma in magnitude. This is magnitude, this is theta, this is pi by 2, this is theta m. So this was, you recall, this was equal to delta theta, and my complete bandwidth was this whole range, 2 delta theta. Okay, so recall this delta theta was equal to pi by 2 minus theta m. 2 delta theta is equal to pi minus 2 theta m, and my fractional bandwidth, so this pi by 2, I also call that equal to theta 0. Yeah, so fractional bandwidth equal to delta f upon f0, it is equal to 2 delta theta upon theta 0, which is equal to pi minus 2 theta m over pi by 2, and this comes out to be equal to 2 minus 4 theta m upon pi. Okay, so this we had already derived it, I am deriving it once again. So coming back to the definition of gamma m, okay, say we defined gamma m, a certain gamma m at theta equal to theta m. Say we know what is the value of gamma m, how can we find out the value of theta m? So this is fairly simple. We can proceed from this equation. If we proceed from this equation, then we can get the value of theta m is equal to cos inverse gamma m upon modulus of gamma L, like this. So from here we can get the value of theta. Okay. So this is this equation. So this is how we can find out the value of theta m, and from here we can find out the value of bandwidth. Just substitute, because this bandwidth is determined by only one unknown, which is theta m, and we found out theta m using the previous equation, and from here we can find out what is the fractional bandwidth. All right. Now, what might be obvious here is that the value of theta m becomes lesser with increasing value of n, capital N, which in turn implies that my bandwidth increases. So theta m decreases with increase in n. So fractional bandwidth will increase with increase in n, which in turn verifies in another way what I had already stated, that the bandwidth, the higher the value of n, capital N, the higher will be the bandwidth. And I had also said that, as we shall see in a few moments, that the value of n, capital N, determines the number of sections in the multi-section transformer. Okay. So let us come back to our equation for the input reflection coefficient of a multi-section transformer that we had derived in the previous part. Okay, so if there are n sections in a multi-section transformer, then the formula is given like this, which in turn can be written like this. So here I'm doing the binomial expansion. Okay, so this is the expression for the input reflection coefficient that we had derived in the last part. And sorry, this is not the equation that we have derived in the last part. This is simply the expansion of the prototype function, of the binomial prototype function, using the binomial theorem. Okay, so let's make this correction. This is not the formula that we had derived in the previous part. This is just an expansion of this binomial formula for the prototype function. But in the previous, now coming to the expression that we had indeed derived in the previous part, it was something like this. And recall, I had said that this is very similar to a Fourier series. Now see the similarity between these two equations. Just by looking, we can directly say that gamma, just by comparing the two equations, we can directly say that gamma k is given by, fine. Now what are the conclusions we can observe, or what are the observations of this expression? First is that the values of gamma k are symmetric. That is because this nck is equal to nck minus 1. Okay. Nc, sorry, not k minus 1, n minus k. So for example, if n equal to 2, then k equal to 1 and sorry, k, not k equal to 1, k equal to 0, and for k equal to 0 and k equal to 2, my gamma k will be same. Second observation is that these quantities, these combinatorial terms, will always be positive, but this gamma L can be negative or positive depending on the values of RL and Z0, isn't it? Because gamma L is given like this. So if RL is greater than Z0, then gamma L is negative. If RL is greater than Z0, then gamma L is positive, and if RL is lesser than Z0, then gamma L is negative. So if that is the case, then that means that See, for gamma case, the gamma L and this term 2 raised to minus n, they remain the same. Only this term, this nck, varies with k. So in other words, depending on whether this gamma L is positive or negative, gamma k's will be either all positive or all negative. If that is the case, then from the expression for gamma k, recall what is gamma k? If all gamma k's are positive, then it means every zk plus 1 is greater than every zk. If all gamma k's are negative, that means every zk1 is lesser than every zk. So it means that if suppose that is the way it is, that all zk's, all subsequent zk's are lesser than the previous one, then that means the width of the multi-section transformer will sort of keep on increasing like this. So your transformer will have a shape like this. On the other hand, if every subsequent zk is greater than the previous one, then the opposite will happen. The width of the subsequent stages will keep on decreasing. You get a shape like this. Now this, when we discuss Chebyshev, that will not be the case. So for binomial, these are the two properties. Okay. First of all, the gamma k's are symmetric and zk's are either uniformly increasing or uniformly decreasing. Now coming back to, okay, these are nice equations where we have found the expression for gamma k's in terms of gamma L and k. We still have not found the values of the zk. So let us see for n equal to 2, say n equal to 2, say we take n equal to 2, okay, and let us write down all the equations. So we will start with, so we will have k equal to 0, 1 and 2, right? So we will have gamma, so starting from this equation, we will have gamma 0 is equal to 2 raised to minus n. That's n is equal to 2. 2C0 gamma L, okay, which in turn is equal to, let's see, it is 1 by 4 is RL minus Z0 upon RL plus Z0, okay. Then we have gamma 1 is equal to 2 raised to minus 2, 2C1 gamma L, which is equal to 1 by 2 RL minus Z0 upon RL plus Z0, okay. And finally we have gamma 2 is equal to 2 raised to minus 2, 2C2 gamma L, which is equal to 1 by 4 RL minus Z0 upon RL plus Z0, and then substituting the value of gamma 0 here, I can write this as Z1 minus Z0 upon Z1 plus Z0. This is equal to Z2 minus Z1 upon Z2 plus Z1. This is equal to Z is equal to RL minus Z0. Sorry, it is equal to RL minus Z2 upon RL plus Z2. So now here the number of unknowns or the unknowns are actually Z1 and Z2, isn't it? So for n equal to 2, our transformer will look something like this. These are the unknowns. So the question is, when the number of unknowns is 2, yet we have 3 equations. This is actually more than the number of equations that we need to solve for Z1 and Z2. And if the problem with these 3 equations is that if we say take these 2 equations to solve for Z1 and Z2, then the solutions will be different if we had taken the first 2 equations. So then how do we resolve this problem? So once again, the problem is that we have 3 equations when our number of unknowns is 2, and if we take any one pair of equations to solve the 2 unknowns, the solution that we obtain from that pair will be different from the solutions for the 2 unknowns Z1 and Z2 that we will obtain when we take a different pair. So to get consistent solutions over whichever pair of equations that we take, what we can do is we take to that simplification for gamma k that we did in the previous part. So what I mean is, let us take gamma k you can try that out. I leave it as an exercise for you. You can try to find out the value of Z1 and Z2 when you take only these 2 equations, and you can try to find out the value of Z1 and Z2 when you say take these 2 equations, and you can also try to find out the values of Z1 and Z2 when you take these 2 equations. You will observe that the solution for Z1 and Z2 will be different for each case. Okay, so now coming back to the simplification, recall the simplification that we used for gamma k, that gamma k given by this formula can be approximated like this. Now let us see what happens when we do this simplification. Okay, so first of all, gamma 0 becomes half ln z1 upon z0. Okay, gamma 1 becomes equal to half ln z2 upon z1, and gamma 2